Okay, guys, this is our last 4-2 video that we're going to do. This is practice after 4-2, so we're going to start by reviewing exponential functions in their graphs. We are going to graph a parent function, f of x equals 2 to the x, on the same set of axes as the transformed function, g of x equals 2 to the x plus 2 minus 4. Our parent function, f of x equals 2 to the x. Well, we know that an exponential function has a domain of all real numbers. That's going to stay the same even when I move over here to the transformed function. This particular function is base 2. If I think about my set of ordered pairs that I'm going to graph, I start with those x values, -2, -1, 0, 1, 2. And I apply these as exponents to 2. So I get 1/4, 1/2, 1, 2, and 4. And I need to graph these values, where x is -2, y is 1/4, x is -1, y is 1/2, x is 0, y is 1. There's my y-intercept. X is 1, y is 2, x is 2, y is 4, and we start our exponential increase. So we have our asymptote we found, and we have our exponential increase. I'm going to go ahead and put in my horizontal asymptote at 0. So horizontal asymptote at y equals 0. My range is limited by that horizontal asymptote, so it is 0 to positive infinity, and my y-intercept is 1. X is 0, y is 1. Now let's look at our transformed function g of x and graph it on the same set of axes. Domain of any exponential function is going to be all real numbers, so I can plug that in immediately. I need to think about what transformations I'm doing. I'm going to move this function to the left 2 and down 4. To do this, I take that y-intercept and I shift it to the left 2 and then down 4, and it ends up here at -2, -3. That's the location of this point when I transform it to the left 2 and down 4. The other thing I move is my asymptote. My asymptote, left or right doesn't matter because it's a horizontal line. That down 4 absolutely matters. So it goes from 0 to -4. 1, 2, 3, 4. So there is my new horizontal asymptote for my transformed function at y equals -4. That is going to determine the range of my transformed function. I need to have this same shape shifted left and down. It finds the asymptote and it curves up. Now, I sketched it without checking my y-intercept first. Let's see how close we got. Our range is limited by that horizontal asymptote at -4. The y-intercept happens where x is 0. So if we do g of 0, we have 2 to the 0 plus 2 minus 4. Well, that's 2 squared is 4 minus 4, which is 0. It should go through the origin. Oh, look at that. We got lucky. It goes through the origin. I should have checked that value before I sketched my graph. Okay, now let's think about logarithmic functions. We've got two logarithmic functions to graph, a parent function base 3 and a transformed function also base 3. We're going to start with the parent log function. The easiest way to graph a log function is to think about the exponential function that would give you those values and then switch them. So if I'm going to do log base 3 of x, well, what I would have plugged in here on the x is now my set of y values. And I've got base 3. So 3 to the -2 is 1/9. 3 to the -1 is 1/3. Anything to the 0 is 1. 3 to the first is 3. 3 squared is 9. These are the coordinates for the points I need to sketch for this log function. Now the log function is the inverse of the exponential function. For the exponential function, the domain is always all real numbers. For the log function, the range is always all real numbers. And then the domain here is limited by my vertical asymptote. Let's sketch these points and see what this parent function looks like. Where x is 1/9, y is -2. So I'm down here. Where x is 1/3, y is -1. Where x is 1, y is 0, we have an x-intercept for a log function. Where x is 3, 1, 2, 3, y is 1, and where x is 9, or y is going to be just up here to 2. So I'm not going to worry about extending that. I just know that I've got this kind of increase that's going right there with a vertical asymptote here at x equals 0. That vertical asymptote limits my domain, so my domain is from 0 to positive infinity. X-intercept right there, where x is 1, y is 0. Okay, now let's transform this function. When I look at my pattern of transformations for g of x, I see that I'm shifting to the right 3, and I'm shifting, let me start over. I'm shifting up 3, and I'm shifting to the right 2. That's my horizontal shift, right 2. That's my vertical shift, up 3. All right, so I'm going to take this point. I'm going to shift it to the right 2, 1, 2, and up 3, 1, 2, 3. The location of it ends up at 3, 3 when it goes to the right 2 and up 3. And then I'm going to take my asymptote. Up or down doesn't matter because it's a vertical asymptote, but that right 2 absolutely matters. So it goes from 0 to 2. So there's my vertical asymptote for this transformed function at x equals 2. That limits the domain. The domain is going to be limited from 2 to positive infinity. So I take my asymptote in that point that I moved, and I'm going to sketch my function, my transformed function. Now the x-intercept, I can visually see that the x-intercept occurs between 2 and 3. If I want to actually calculate that, I would set y equal to 0. So I would say 0 is equal to 3 times, or 3 plus log base 3 of x minus 2. We're not gonna worry about calculating that x-intercept right now. We know it's going to be something between 2 and 3. Let's look at the back. Writing each log equation in its equivalent form. That means that writing each equation in its equivalent form, whether it is log or exponential. If I start with a log equation, I write it in exponential form. So right here, I've got base, argument, exponent. Base 2, exponent 6 is an argument of 64. Let's finish the log statements. Number 7 is a log statement. My base is m. The answer to the log is always the exponent. That means the argument is 32. And I've got one more logarithm. My base is 9. The answer to the log statement is the exponent, so the argument is x. I'm not asked to do anything else. Just write it in the equivalent form. Now let's go back to our exponential forms and write them as log statements. So log, my base here is 5. The answer is going to be the exponent, so I put the argument there. So log base 5 of 625 is 4. Log base, well, my base is 8, of the argument is equal to the exponent y. And finally, log, my base is 5, my argument is 1 over 125, is equal to the exponent negative 3. The final problems, 9 through 18, says to evaluate without using a calculator. Evaluate without using a calculator. I'm asked to solve this logarithm. Remember, the answer to the log is always the exponent. What is the exponent of 4 that gives me 16? Well, it's 2. What is the exponent of 6 that gives me 1? Well, anything to the 0 power is 1. What's the exponent of 5 that gives me 1 over 5? Well, to find the reciprocal, I used a negative 1. What's the exponent of 8 that gives me 8? Just 1. What's the exponent of 81 that gives me 9? Ooh, look at that, I'm getting smaller. If I'm getting smaller, I'm taking the root. In this case, I'm taking the square root, so my exponent would be 1/2. I don't have a base written. So if I don't have a base written, what is my base? Log log is base 10. So 10 to some power gives me that argument 10 to the 7th. What's my missing piece? It's 7. Again, log log, no base written, is base 10. 10 to what exponent gives me 1,000? Well, I've got 3 zeros, so that would be base 3. Natural log, ln, is base e to some power, gives me that argument, e to the 9x. Well, my missing piece is that 9x. Natural log again, base e to some power gives me 1. Well, anything raised to 0 is 1. And natural log is base e to some exponent gives me e. What's my missing piece? It's just 1.